The James Webb Space Telescope just found something that's making scientists uncomfortable, really uncomfortable. 6 months into its mission, Webb started sending back images of galaxies that shouldn't exist. Not according to fringe theories or wild speculation, but according to our most fundamental understanding of how the universe works. These galaxies appeared too massive, too bright, too organized for objects that formed just a few 100 million years after the Big Bang. Within weeks, papers started appearing with titles containing words like crisis and impossible. Some researchers began openly questioning whether we needed to rewrite cosmology itself. But here's what makes this story different from typical scientific controversies. This isn't about one anomalous data point that might go away with better measurements. It's about dozens of galaxies, all telling the same impossible story. And the deeper Webb looks, the stranger things get. Let me take you back to December 25th, 2021. That's when humanity launched the most expensive, most complex, most powerful telescope ever built into space. $10 billion, 30 years of development, a mirror so large it had to fold like origami to fit inside the rocket. The telescope traveled to a point 1.5 million kilometers from Earth, 4 times farther than the Moon, where it would spend the next decade peering deeper into space and time than any instrument in history. The mission was straightforward, at least on paper. Study the first galaxies born after the Big Bang. Watch planets form around distant stars. Analyze the atmospheres of alien worlds. Standard astronomy stuff, just with unprecedented clarity and reach. Nobody expected Webb to immediately challenge the foundations of modern cosmology. The trouble started almost as soon as the telescope opened its golden eye. Astronomers began identifying galaxies at distances that pushed the boundaries of the observable universe. Galaxies existing just 280 million years after the Big Bang. Then 235 million years. Each discovery set a new record. Each image revealed structures that looked eerily mature for their cosmic age. At first, excitement dominated the conversation. Breaking records is what new telescopes are supposed to do. But as the data accumulated, excitement gave way to confusion. These early galaxies weren't just setting distance records. They were violating fundamental predictions about how galaxies should behave in the infant universe. The galaxies were too bright. Way too bright. According to the Lambda CDM model, the standard framework that's guided cosmology for decades, early galaxies should be small, dim, and messy. They should be struggling to pull themselves together from the primordial gas that filled the young universe. Instead, Webb was showing us galaxies blazing with the light of billions of stars, packed into regions far smaller than our own Milky Way. One galaxy in particular stopped astronomers in their tracks. They named it JADES-GS-Z14-0. And it existed when the universe was barely 280 million years old. To put that in perspective, if the universe's current age of 13.8 billion years was compressed into a single year, this galaxy would have formed on January 6th, before noon. This galaxy wasn't just bright. It was impossibly organized. It showed signs of complex chemistry, indicating multiple generations of stars had already lived and died. Stars that manufactured elements heavier than hydrogen and helium. Stars that exploded as supernovae, enriching the surrounding gas with the building blocks of planets and, eventually, life. But wait. How could multiple generations of stars live and die in just 280 million years? That's barely enough time for one generation to form, burn through its fuel, and explode. The math didn't work. The timeline was too compressed. Then came the mass estimates. When astronomers calculated how much matter these early galaxies contained, the numbers made no sense. Some appeared to contain as much mass as our entire Milky Way, despite existing when the universe was less than 2% of its current age. The Milky Way took billions of years to assemble its mass through countless mergers and steady star formation. These galaxies seem to have accomplished the same feat in a cosmic eye blink. The scientific papers started piling up. Titles like A Population of Red Candidate Massive Galaxies and Impossibly Early Galaxy Candidates at Z greater than 8 appeared in journals. One study identified 6 galaxies so massive they contained 100 times more matter than theoretical models predicted should be possible. Another found that early galaxies were forming stars at rates 1,000 times higher than the Milky Way's current pace. Scientists don't use the word impossible lightly. In physics, impossible usually means one of 3 things. Either your measurements are wrong, or your theory is wrong, or something very interesting is happening that you don't understand yet. The measurements weren't wrong. Webb's instruments are the most precisely calibrated ever sent to space. Its infrared sensors can detect temperature differences of thousandths of a degree. Its spectrographs can analyze the chemical composition of galaxies billions of light years away with stunning accuracy. When Webb says it's seeing something, you can trust it's really there. So if the measurements were solid, maybe the theory was broken. This possibility genuinely worried cosmologists. The Lambda CDM model has explained countless observations over decades. It predicted the cosmic microwave background radiation pattern we observe. It explained how galaxies cluster across vast distances. It described the expansion rate of the universe. Throwing out this model would mean losing our fundamental framework for understanding cosmic evolution. Some researchers started exploring radical alternatives. Maybe dark matter behaves differently than we thought. Maybe gravity works differently on cosmic scales. Maybe the Big Bang itself needs revision. Conference presentations became heated. Online forums filled with debate. A few scientists started using phrases like crisis in cosmology. Then something unexpected happened. The crisis started to resolve itself. Not because the galaxies went away or the data changed, but because scientists looked more carefully at what those galaxies actually were. Remember those impossibly bright, impossibly massive early galaxies. Many of them turned out to be hiding a secret. They weren't just collections of stars. They contained supermassive black holes actively devouring matter at prodigious rates. And black holes eating gas put on quite a show. When matter falls toward a black hole, it doesn't just quietly disappear. It forms a swirling disk of superheated material that glows brilliantly across the electromagnetic spectrum. This accretion disk can outshine the entire galaxy of stars surrounding it. From Webb's vantage point, billions of light years away, that black hole light gets mixed together with starlight, making the galaxy appear far more massive and luminous than it really is. Scientists started calling these deceptive objects little red dots because of how they appeared in Webb's images. Small, compact, and glowing with a distinctive reddish hue from dust surrounding the central black hole. Once astronomers identified and removed these little red dots from their analysis, the crisis began to fade. The remaining galaxies, while still surprising, fit much better within existing theoretical frameworks. But here's where the story takes another turn, because even after accounting for the little red dots, even after removing the black hole contamination from the data, a puzzle remained. There were still too many massive galaxies in the early universe. Not impossibly too many, not crisis level too many. Just about twice as many as the standard model predicted. That might sound like a minor discrepancy. It's not. When your theory predicts X and observations show 2X, something interesting is happening. The universe is trying to tell you something about processes you don't fully understand. The explanation might involve something called bursty star formation. Modern galaxies like the Milky Way form stars at relatively steady rates, a few solar masses per year, spread out over billions of years. But early galaxies might have behaved very differently. They might have experienced intense episodes of rapid star formation, creating massive stellar populations in brief cosmic bursts, followed by long periods of relative quiet. Imagine a galaxy that sleeps for tens of millions of years, then suddenly wakes up and forms a billion stars in just a few million years, then goes dormant again. This on-off behavior could explain why early galaxies appear so bright when we observe them. We're catching them during their active phases, their growth spurts. When star formation reaches levels that would seem impossible if sustained over long periods, computer simulations support this idea. When researchers model the early universe accounting for the turbulent, chaotic conditions that existed back then, they find that bursty star formation emerges naturally. Gas clouds collide and collapse. Gravitational instabilities trigger sudden episodes of starbirth. Supernova explosions blow gas out of galaxies, temporarily halting star formation until gravity pulls more material back in. But the simulations also reveal something else. Early galaxies weren't just forming stars in bursts, they were fundamentally different creatures than modern galaxies. They lack the smooth, rotating disk structure we see in galaxies today. Instead, they were turbulent, clumpy, chaotic systems that hadn't yet settled into stable configurations. Astronomers analyzed over 250 young galaxies using Webb's data, studying how gas moved within these ancient systems. Most showed signs of extreme turbulence. Gas wasn't rotating smoothly around galactic centers. It was churning, colliding, creating pockets of intense star formation scattered throughout the galaxy, rather than organized into neat spiral arms. This finding actually strengthened confidence in the standard cosmological model. Previous observations from other telescopes had suggested some early galaxies were already well-organized disks, which didn't match theoretical predictions. But Webb's superior resolution revealed the truth. Those apparently organized galaxies were actually messy, turbulent systems that just looked smooth from farther away. The universe was behaving more like theory predicted, not less. Still, mysteries remained. 3 ultramassive galaxies discovered by Webb, nicknamed the Red Monsters, posed a different kind of puzzle. These galaxies, each nearly as massive as the Milky Way, existed within the first billion years after the Big Bang. They appeared to have converted gas into stars with remarkable efficiency, far exceeding the typical 20% conversion rate predicted by models. In standard galaxy formation theory, dark matter halos capture gas, which slowly cools and condenses into stars. But most of the gas never forms stars. It gets blown away by stellar winds, heated by supernova explosions, or remains too hot to collapse. Yet these red monster galaxies seem to have beaten those odds, turning much more of their gas into stars than should have been possible. The discovery raised questions about physical processes operating in the early universe. Maybe cooling mechanisms worked differently back then. Maybe the first generations of stars behaved unlike modern stars. Maybe feedback processes that regulate star formation today were less effective in the chaotic environment of the infant cosmos. And then there were the black holes. Not just the ones hiding in little red dots, but genuine supermassive black holes existing far earlier than they should. Webb confirmed an actively growing black hole in a galaxy just 570 million years after the Big Bang. This black hole already contained millions of solar masses, which creates a serious timeline problem. The conventional picture of black hole growth starts with massive stars. When these stars die, they collapse into stellar mass black holes containing perhaps 10 to 100 times the Sun's mass. These seed black holes then grow by accreting gas and merging with other black holes over billions of years, eventually becoming the supermassive monsters we observe at the centers of mature galaxies. But 570 million years isn't nearly enough time for this gradual growth process to produce million solar mass black holes. Even if a seed black hole formed immediately after the Big Bang and accreted matter at the maximum theoretical rate, constantly feeding without pause, it couldn't grow large enough fast enough to match what Webb observed. This suggests something different must have happened in the early universe. Maybe the first black holes didn't form from individual massive stars. Maybe they formed directly from collapsing gas clouds, creating much larger seed masses to begin with. Or maybe black holes grew through super Eddington accretion, consuming matter faster than standard physics suggests should be possible. The discoveries just kept coming. Webb found massive black holes lurking in tiny dwarf galaxies. It detected a gamma-ray burst that lasted 7 hours instead of the typical few seconds, suggesting either a new class of cosmic explosion or gaps in our understanding of how stars die. It created the most detailed maps of dark matter ever produced, revealing the invisible cosmic web that shapes galaxy formation. Each discovery added another piece to a puzzle that's still far from complete. The picture emerging from Webb's observations isn't one of cosmology breaking or theories collapsing. It's something more subtle and more interesting. The universe's early chapters were stranger, more violent, and more diverse than we imagined. The standard lambda CDM model survived intact, but the story of how galaxies actually form within that framework needed serious revision. Stars didn't just gradually assemble into galaxies over billions of years. They formed in bursts. They created turbulent, chaotic systems that slowly calmed into ordered structures. They manufactured black holes through processes we still don't fully understand. And here's what keeps astronomers awake at night. Webb has only been operating for a few years. It's designed to function for at least a decade, possibly longer. Every week brings new data. Every month reveals new puzzles. The telescope is still in its infancy, still learning to see with its golden eye. What else is hiding in those ancient galaxies? What other impossible objects are waiting to be discovered? What other assumptions about cosmic evolution will Webb challenge next? The early universe is proving to be far more complex than the simplified models suggested. It was a time of extremes, when physics operated at the edge of what's possible. when the first stars blazed far brighter than modern stars, when galaxies grew through mechanisms we're only beginning to understand. But perhaps the most unsettling aspect of Webb's discoveries isn't what it's found. It's what those findings suggest might exist beyond the edge of the observable universe, in regions so distant that their light hasn't reached us yet. If the galaxies we can see are this strange, this unexpected, what lies in the parts of the cosmos forever beyond our view? The telescope that was supposed to answer our questions about cosmic dawn has instead revealed how little we actually knew. It's shown us a universe that's wilder, more violent, and more mysterious than we imagined. And the story is just beginning, because there's something else Webb found. Something that goes beyond surprising galaxies or unexpected black holes. Something that challenges not just our models of galaxy formation, but our understanding of what kinds of objects can even exist in the universe. And that discovery opens doors to possibilities that sound more like science fiction than science fact. Those objects are called dark stars, not the kind of darkness we're used to, not black holes or cosmic voids. These would be something the universe has supposedly never produced before. Stars powered not by nuclear fusion, but by the annihilation of dark matter itself. The concept sounds absurd. Stars work through fusion. Everyone knows that. Hydrogen atoms slam together under immense pressure and temperature, fusing into helium and releasing energy. That's how stars shine. That's how they've always worked since the first generation lit up the cosmos. But what if there was another way? Dark matter makes up about 27% of the universe's mass energy content. We know it's there because of its gravitational effects on galaxies and galaxy clusters. We've mapped its distribution across the cosmic web, but we've never actually detected a dark matter particle directly. We don't know what it's made of. Some theoretical models suggest dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would rarely interact with normal matter, passing through planets and people like ghosts. But when two WIMPs meet, they could annihilate each other, converting their mass directly into energy, according to Einstein's famous equation. That energy release could, in theory, power a star. Picture the very early universe, just a few million years after the Big Bang. Dark matter is everywhere, far more concentrated than it is today. Gas clouds begin collapsing under gravity, heating up as they compress. Normally, this would lead to fusion once temperatures reach millions of degrees, but before fusion ignites, something else happens. The collapsing cloud drags in massive amounts of dark matter. As the cloud compresses, dark matter particles that have been drifting through space for eons suddenly find themselves packed together at enormous densities. They start colliding, annihilating, pumping energy into the forming star. This dark matter annihilation generates enough heat to halt the collapse and create pressure that balances gravity. The cloud stops shrinking. It forms a stable object radiating energy from dark matter destruction rather than fusion. A dark star is born. These objects would be massive, really massive. Conventional fusion-powered stars have an upper limit around 100 to 150 solar masses. Get bigger than that, and radiation pressure tears the star apart. But dark stars wouldn't face that constraint. They could grow to thousands or even millions of solar masses, fed by continuous dark matter annihilation, and they would be bright, incredibly bright. Dr. Cosmin Illy from Colgate University has been studying this possibility. His team ran simulations showing that some of Webb's most puzzling early galaxies could actually be explained as single supermassive dark stars rather than collections of millions of normal stars. The spectral signatures match. The extreme brightness matches. The existence of these objects at times when galaxies shouldn't have been so developed matches. But here's what makes this truly fascinating. If dark stars existed, they would solve multiple problems simultaneously. Remember those supermassive black holes appearing impossibly early? Dark stars provide a pathway. When a supermassive dark star eventually exhausts the dark matter in its vicinity, it would collapse. Not gradually like normal stars, but catastrophically. The entire million solar mass object would implode, forming a massive black hole in one dramatic event. No need to wait billions of years for black holes to slowly accumulate mass. No need to explain how seed black holes grew so fast. Dark stars could create supermassive black holes directly in the universe's first few 100 million years. The little red dots Webb discovered. Some might be dark stars. Their spectral characteristics, which confused astronomers because they didn't quite match normal stars or standard black holes, could be the signature of dark matter annihilation mixed with some conventional stellar processes, those unexpectedly massive early galaxies. Maybe some aren't galaxies at all, but individual dark stars so bright they were mistaken for entire collections of stars. This isn't just speculation. Multiple research teams have published papers in peer-reviewed journals exploring these possibilities. The Universe Journal recently featured an article detailing how dark star theory aligns with Webb's observations better than conventional explanations in certain cases. But proving dark stars exist requires more than theoretical models. It requires finding definitive observational proof. That's where things get tricky. Dark stars would emit light across a specific spectrum, different from fusion-powered stars. They'd be cooler than you'd expect for their brightness. Their chemical composition would be unusual, lacking the heavier elements that normal stellar fusion produces. Webb's spectroscopic instruments can detect these signatures. Scientists are now combing through Webb's data, looking for objects that match the dark star profile. Several candidates have emerged. Objects that are too bright, too cool, and too chemically primitive to be normal stars. Objects that could only exist if powered by something other than fusion. The confirmation process takes time. Each candidate requires detailed analysis, ruling out every possible conventional explanation. But if even one object is confirmed as a dark star, it would revolutionize astrophysics. We would have direct evidence of dark matter interactions beyond gravity. We'd finally know what dark matter does when it's concentrated enough to affect stellar evolution. We'd understand how the universe's first supermassive structures form so quickly, and we'd have proof that the cosmos contains objects fundamentally different from anything we've studied before. But dark stars represent just one possibility among several competing theories trying to explain Webb's observations. Another idea gaining traction involves primordial black holes. These wouldn't form from dying stars, but would have been created directly in the Big Bang's aftermath. Extreme density fluctuations in the first fraction of a second could have produced black holes of any size, from microscopic to supermassive. If the early universe contained numerous primordial black holes, they could have served as seeds that quickly grew into the supermassive monsters Webb observes. They could also have affected early galaxy formation in ways standard models don't account for, potentially explaining why those galaxies appear so developed. Then there's the possibility that stellar physics worked differently in the early universe. Lower metallicity gas, different radiation environments, and stronger gravitational fields might have allowed stars to form faster and more efficiently than modern stars can. Computer simulations exploring this scenario show that under early universe conditions, gas could collapse into stars in just tens of thousands of years rather than millions. Star formation efficiency could have reached 50% or higher compared to the 10 to 20% typical today. That would make early galaxies appear far more massive and bright than expected. Some researchers propose that the first stars were fundamentally different from modern stars. Population 3 stars, as they're called, formed from pristine gas with no heavy elements. Without metals to cool the gas efficiently, these first stars might have been much more massive than any star forming today. Masses of 300 solar masses or more aren't unreasonable for population 3 stars. Such giants would burn through their fuel in just a few million years, but they'd be incredibly luminous during that brief life. A single one could outshine millions of modern stars combined. If early galaxies contained more population 3 stars than models predicted, that alone could explain much of Webb's data without invoking dark stars or primordial black holes. Each theory has strengths, each has weaknesses, and they're not mutually exclusive. The early universe might have featured dark stars and primordial black holes and super-efficient star formation all operating simultaneously. The challenge facing astronomers is distinguishing between these possibilities using limited observational data. Webb's spectroscopy provides clues. Different scenarios produce different chemical signatures. Dark stars should show unusual element ratios. Primordial black holes would affect surrounding gas in specific ways. Population 3 stars would have distinctive spectral features, but the objects are so distant and so ancient that extracting clear signals remains difficult. Redshift stretches their light into infrared wavelengths where Earth's atmosphere interferes. Cosmic dust obscures details. The objects themselves are small and faint despite their intrinsic brightness. Still, progress continues. Recent observations have started constraining the possibilities. Some candidate dark stars have been ruled out as extremely distant normal galaxies. Some apparent early supermassive black holes have been confirmed through multiple independent observations. The picture gradually sharpens. What's becoming clear is that the early universe operated under more extreme and varied conditions than simplified models suggested. Multiple formation pathways likely contributed to the diverse population of objects Webb observes. Some early galaxies probably did assemble quickly through conventional but highly efficient star formation. Others might host growing supermassive black holes that amplify their brightness. A few could be dark stars or other exotic objects we haven't fully characterized yet. The universe doesn't restrict itself to single explanations. It explores every available possibility, creating the full spectrum of objects that physics allows. And that brings us to perhaps the most unsettling implication of Webb's discoveries. If these exotic objects existed in the early universe, they might still exist today. Dark stars would have finite lifetimes, eventually collapsing once their dark matter fuel ran out. but some might persist in extreme environments where dark matter concentrations remain high. Primordial black holes, if they exist, would be indistinguishable from black holes formed by dying stars. They could be scattered throughout every galaxy, including our own, hiding in plain sight among the stellar remnants we've already catalogued. Even population 3 stars might still form occasionally in rare pockets of pristine gas that somehow avoided contamination with heavy elements for billions of years. The cosmic bestiary might be far richer and stranger than we've assumed. Webb has shown us that the infant universe contained objects that challenge our understanding of what's possible. Those same objects, or their descendants, could be lurking in the modern cosmos, waiting to be recognized for what they really are. This realization leads to an uncomfortable question. How many other exotic objects exist that we haven't discovered because we weren't looking for them? Astronomers catalogue millions of stars and galaxies. We classify them based on established categories derived from decades of observation. But those categories were developed studying objects in the nearby, well-evolved universe. They might not encompass everything that exists. There could be dark stars shining in distant galaxy clusters, primordial black holes drifting through interstellar space, relic objects from cosmic dawn that don't fit any known classification. We wouldn't recognize them as unusual because we're not searching for signatures we don't expect to find. Webb is changing that. By revealing how strange the early universe actually was, it's forcing astronomers to broaden their perspective, to look at familiar objects with fresh eyes, to consider possibilities that seem too exotic to take seriously just a few years ago. And the telescope is just getting started. Years of observations lie ahead. Deeper surveys, more detailed spectroscopy, systematic searches for specific exotic object signatures. Each new dataset brings potential discoveries. Each analysis could reveal something that shouldn't exist according to conventional theory. The revolution Webb sparked is still accelerating, still uncovering layers of cosmic strangeness that nobody predicted. But there's something else Webb found that goes beyond unusual objects or unexpected formation processes, something that challenges our understanding at an even deeper level, something that hints at physics we haven't discovered yet, operating in the universe's earliest moments. That something appears in the patterns themselves, in the distribution of galaxies, in the clustering of matter across cosmic scales, in the way structure assembled during those first crucial billion years. Webb's surveys reveal something disturbing when you map enough galaxies. The distribution isn't quite what our best simulations predict. There are subtle differences in how matter clumped together, regions that became too dense too quickly, voids that formed with unexpected precision, patterns that suggest the early universe operated under slightly different rules than we assumed. These aren't measurement errors. Multiple independent surveys confirm the same basic picture. The cosmic web, that vast network of filaments connecting galaxy clusters, shows features in Webb's high-resolution data that don't perfectly match what emerges from our simulations of cosmic evolution. Something influenced how matter distributed itself across space. Something shaped the architecture of cosmic structure in ways our models don't fully capture. The obvious culprit is dark matter. We know it exists. We've measured its gravitational effects for decades. Our entire cosmological framework depends on dark matter shaping the distribution of ordinary matter through gravity alone. But what if dark matter does more than just exert gravitational pull? What if it interacts with itself in subtle ways we haven't detected? What if its properties change slightly as the universe evolved? These aren't wild speculations. They're serious proposals from cosmologists trying to reconcile Webb's observations with theoretical predictions. The standard cold dark matter model assumes dark matter particles barely interact with anything, including each other. They form halos through gravity. They provide scaffolding for galaxies. They do nothing else. That simplicity has served cosmology well. It explains galactic rotation curves. It accounts for gravitational lensing observations. It produces cosmic microwave background patterns that match reality with stunning precision. But simplicity isn't always truth. Nature rarely chooses the most elegant option when messier alternatives work just as well. And Webb is suggesting that dark matter might be slightly messier than we thought. Consider what happens if dark matter particles can interact with each other through some force we haven't discovered. Not frequently. These interactions would need to be rare enough that we haven't detected them in our experiments. But occasionally, under specific conditions that existed in the early universe, such interactions could alter how dark matter halos formed. They might cause dark matter to concentrate differently, to create slightly different density patterns, to influence structure formation in subtle ways that become visible only when you can observe the universe at cosmic dawn with sufficient resolution. Webb's data hints at exactly these kinds of effects. Galaxy distributions that suggest dark matter concentrated more efficiently in certain regions. Cosmic web patterns that indicate dark matter filaments formed slightly differently than pure gravitational collapse would predict. Structures that seem to remember processes that occurred before the first stars lit up. This doesn't mean the standard model is wrong. It means it might be incomplete. Dark matter could have properties beyond what we've incorporated into our simulations, additional physics operating at scales or energies we haven't probed experimentally. The implications extend beyond cosmology. If dark matter has hidden complexity, that affects particle physics predictions. It changes what we should look for in detection experiments. It suggests that the dark sector, the realm of particles that don't interact electromagnetically, might contain entire force hierarchies we've never imagined. But there's another possibility that's even more unsettling. What if the patterns Webb sees reflect not dark matter complexity, but something more fundamental? What if the early universe experienced conditions that altered how physics itself operated? Physicists have long suspected that the laws of nature might not be entirely constant. The fundamental constants that determine particle masses, force strengths, and interaction rates. These numbers seem arbitrary in our current theories. We measure them, we plug them into equations, but we don't know why they have the specific values they do. Most cosmologists assume these constants have remained fixed since shortly after the Big Bang. Once the universe cooled below certain energy thresholds, the values froze. They've been unchanging for nearly 14 billion years. But what if that assumption is wrong? What if some constants evolved gradually as the universe expanded and cooled? What if the physics operating at cosmic dawn was subtly different from the physics we measure in laboratories today? Webb's observations can't prove this directly. You can't measure fundamental constants in distant galaxies with enough precision to detect tiny variations, but you can look for their consequences. for patterns in cosmic structure that shouldn't exist if physics remained perfectly constant, for galaxy formation processes that work slightly more efficiently than they should, for distributions of matter that suggest different rules were in play. And that's exactly what some researchers claim to see in Webb's data. Not definitive proof, cosmology rarely offers that, but tantalizing hints, statistical patterns that become easier to explain if you allow certain constants to vary by tiny amounts in the early universe. The most controversial proposal involves the fine structure constant. This dimensionless number governs electromagnetic interaction strength. It's one of the most precisely measured constants in physics, and it's supposed to be absolutely unchanging. But analyses of quasar spectra, light that passed through gas clouds billions of years ago, have occasionally suggested minuscule variations. These claims remain hotly disputed. Most physicists dismiss them as systematic errors or misinterpretations of complex data. Webb might finally settle the debate. Its spectroscopic capabilities exceed anything available before. It can measure absorption lines in distant quasar light with unprecedented precision. If the fine structure constant varied in the early universe, Webb should detect the signature. Early results are ambiguous. Some analyses find hints of variation. Others show nothing unusual. The datasets remain limited. More observations are needed before anyone can draw firm conclusions. But even the possibility changes how we think about cosmic evolution. If fundamental constants weren't truly constant, that opens doors to physics beyond the standard model. It suggests the universe's history might be richer and stranger than textbooks describe. It means the infant cosmos didn't just contain different objects than today's universe. It might have operated under different rules. The philosophical implications are staggering. We assume the laws of physics are universal, that an electron in a galaxy 10 billion light-years away behaves identically to an electron in a laboratory on Earth, that gravity works the same everywhere and everywhen, that we can trust our observations and measurements across cosmic distances. If constants vary, even slightly, that universality becomes questionable. Not in ways that matter for everyday physics or engineering. The variations would be far too small to affect anything on human scales. But for cosmology, for understanding the universe's history and evolution, even tiny changes in fundamental constants could matter enormously. They would affect how stars formed, how galaxies assembled, how structure emerged from the primordial density fluctuations. Every process that depends on precise balances between different forces, which includes essentially everything in astrophysics, could be altered by constant variation. This leads to an uncomfortable realization. Our entire understanding of cosmic history rests on extrapolating laws we measure today backward across billions of years. We assume the universe has always played by the same rules. We build our theories and simulations on that foundation. Webb is questioning that foundation, not overturning it. The evidence isn't there yet, but raising doubts, showing us phenomena that don't quite fit, forcing us to consider possibilities we'd previously dismissed as unnecessarily complicated or philosophically troubling. The alternative is accepting that the early universe simply worked differently than we understand. That galaxy formation proceeded through mechanisms we haven't identified. That structure assembled via processes we haven't modeled. That our theories, while impressive, remain incomplete. This shouldn't be surprising. Cosmology is barely a century old as a quantitative science. We've been able to observe the distant universe in detail for only a few decades. The tools that let us peer back to cosmic dawn, telescopes like Webb, have existed for mere years. We've made astonishing progress. The fact that our models work as well as they do, that we can predict the cosmic microwave background's detailed features, that we understand structure formation well enough to simulate galaxy evolution, these are extraordinary achievements. But they're not complete achievements. Every successful scientific theory eventually reveals its limitations. Newton's gravity worked beautifully until it didn't. Maxwell's electromagnetism seemed complete until quantum mechanics arrived. Einstein's relativity transformed our understanding but still doesn't play nicely with quantum theory. Our current cosmological model will face similar boundaries. Webb is helping us find them. Every observation that doesn't quite match predictions, every galaxy that forms too efficiently, every structure that appears too early. These aren't failures of science. They're opportunities to refine our understanding, to discover what we've been missing. And what we've been missing might be profound. Not just details about how galaxies formed, not just corrections to star formation models or dark matter properties, but fundamental insights into how the universe operates at its deepest levels. The patterns Webb reveals in the distribution of early galaxies suggests something influenced cosmic evolution beyond what our simulations include. Whether that something is dark matter complexity, varying constants, or physics we haven't imagined yet remains unknown, but it's there. In the data, in the patterns, in the subtle discrepancies between what we observe and what we predict. Webb has given us a puzzle that goes beyond exotic objects or unexpected formation processes. It's shown us that the universe's history might be written in a language we're still learning to read, that the first billion years after the Big Bang might have unfolded according to principles we don't fully grasp. That cosmic dawn, rather than being a simpler, more primitive version of today's universe, might have been its own unique epoch with its own distinct physics. And that's not a comfortable place for science to be. When your best theories explain most things beautifully but leave glaring exceptions, you face a choice. Dismiss the exceptions as observational errors, which becomes harder when they multiply. Or accept that something fundamental needs revision. Webb's data has pushed astronomers toward that second option. The telescope has catalogued dozens of galaxies from the universe's first billion years. Each one tells a similar story: too bright, too structured, too efficient at turning gas into stars. These aren't random outliers scattered across the sky. They're everywhere. Webb looks at those extreme distances. Statistical flukes don't behave that way. Systematic problems with observations don't either, since independent teams using different methods keep arriving at the same conclusions. What we're witnessing might be the early stages of a paradigm shift, not the dramatic collapse of cosmology that some headlines proclaimed, but something potentially more significant: the recognition that the infant universe operated under conditions we haven't adequately modeled. Consider the red monsters. 3 ultramassive galaxies identified within the first billion years after the Big Bang, each approaching the Milky Way's total mass. Standard galaxy formation theory says only about 20% of available gas converts to stars in early galaxies. The rest gets blown away by stellar winds, supernovae, or simply fails to collapse. That inefficiency is built into every simulation. calibrated against observations of more recent galaxy formation. The red monsters converted their gas at dramatically higher efficiency. Perhaps 40, 50, even 60% transformed into stars. That shouldn't happen according to the physics we understand. Young galaxies should be messy, turbulent, wasteful. They should struggle to retain their gas against the violent feedback from massive stars exploding in rapid succession. Unless feedback worked differently back then. Unless the gas itself had properties that made it easier to convert. Unless dark matter halos provided deeper gravitational wells than our models suggest. Unless something about the early universe's density, temperature, or chemical composition fundamentally altered how star formation proceeded. Each unless represents a potential avenue for new physics. And here's where Webb's discoveries become particularly intriguing. They're pointing toward multiple independent lines of evidence suggesting the same conclusion. The early universe wasn't just different in one specific way, it was comprehensively different across several fundamental processes. Take the turbulence findings. Webb examined over 250 galaxies from 800 million to 1.5 billion years after the Big Bang. Most showed chaotic, clumpy structures, turbulent systems that hadn't settled into smooth, rotating disks, gas moving in random directions rather than orderly circular orbits, stars forming in scattered bursts rather than steady spiral arms. That matches theoretical expectations for young galaxies. Frequent mergers, intense star formation, powerful stellar feedback. All should create turbulent conditions. The surprise came from how extreme the turbulence was and how long it persisted. Simulations predicted galaxies would settle faster, developing rotation and structure earlier than what Webb observes. But slow settling means extended periods of inefficient star formation. Turbulent gas doesn't collapse easily. It creates stars in fits and starts, wasting most of its potential, which directly contradicts what the red monsters demonstrate: exceptional efficiency at converting gas to stars. You can't have both extreme turbulence and exceptional efficiency. Not with the same physics. Either the red monsters aren't as turbulent as similar mass galaxies from that era, suggesting some special formation pathway, or turbulence doesn't inhibit star formation as much as we think in early universe conditions. Or we're missing some mechanism that occasionally allows even turbulent galaxies to undergo brief periods of extraordinary star formation. That last option connects to another Webb finding: bursty star formation. Supercomputer simulations, accounting for the early universe's specific conditions, showed stars could form in sudden rapid bursts separated by quiet periods. The gas would accumulate during quiescence. Then something would trigger simultaneous collapse across large regions. Thousands of stars igniting essentially at once, creating intense brightness before the feedback shut everything down again. If galaxies cycle through these bursts, their time average star formation rate would look modest. But catch them during a burst, and they'd appear extraordinarily bright and active. That could explain why Webb sees so many luminous early galaxies without requiring fundamental changes to cosmology, except the math doesn't quite work. Even with maximally optimistic assumptions about burst frequency and intensity, simulations struggle to match the sheer number of bright galaxies Webb observes. You can get some of them, maybe even most, but not all. Not with the distribution and properties Webb measures. Which brings us back to those little red dots. compact objects scattered throughout Webb's deep images of the early universe. Initially classified as tiny but remarkably bright galaxies, possibly containing unexpectedly massive black holes. Recent analysis suggests they might be something even stranger: supermassive stars. Not just big stars, supermassive stars. Objects thousands of times heavier than the Sun, powered not by fusion but by dark matter annihilation. Hypothetical objects proposed decades ago but never observed, until possibly now. The theory goes like this. In regions where dark matter density was exceptionally high, particles would occasionally collide and annihilate, producing energy. That energy could support a star against gravitational collapse without requiring nuclear fusion. Such stars could grow vastly larger than fusion-powered stars, accumulating mass without the usual limits imposed by radiation pressure. These supermassive dark stars would be incredibly luminous, explaining some of the unexpected brightness Webb sees. They'd also be short-lived, eventually collapsing into massive black holes once the dark matter fuel depleted. Those black holes would then serve as seeds for the supermassive black holes we observe in galaxy centers today, solving another major puzzle about how such massive black holes formed so quickly. It's an elegant solution, perhaps too elegant. The conditions required for dark star formation are extremely specific. You need dark matter densities higher than most simulations predict for the early universe. You need the dark matter to have particular properties that allow significant annihilation rates. You need the environment to support these objects long enough to grow massive, but not so long they consume all available dark matter before collapsing. Every requirement is possible, none is certain, and the entire framework rests on dark matter having properties we haven't confirmed. We know dark matter exists through its gravitational effects. We don't know what particles comprise it, or how those particles interact with each other beyond gravity. If dark stars explain the little red dots, that's simultaneously exciting and troubling. Exciting because it would represent the first direct detection of dark matter particles through their annihilation signature, rather than just gravitational influence. Troubling because it would mean dark matter is more complex and active than minimal models suggest, potentially affecting numerous other astrophysical processes we thought we understood. And the little red dots might not even need dark stars to explain them. Alternative proposals suggest they're actually supermassive black holes accreting gas rapidly, surrounded by dusty envelopes that produce their distinctive spectral signatures. Or they could be dense stellar clusters, thousands of stars packed into tiny regions, collectively generating enormous luminosity. Each interpretation carries different implications. Black holes mean we need faster black hole growth mechanisms. Stellar clusters mean we need processes that concentrate stars far more efficiently than modern galaxies achieve. Dark stars mean we need to revise our understanding of dark matter. The data doesn't yet distinguish between these possibilities. That's where we are. Multiple competing explanations for phenomena we barely understand, each requiring some aspect of cosmology or astrophysics to work differently than we expected. Webb has also spotted supermassive black holes in dwarf galaxies. Tiny galaxies with masses far below what typically hosts such enormous black holes. The relationship between galaxy mass and central black hole mass is one of the tightest correlations in astrophysics. Bigger galaxies have proportionally bigger black holes, following a predictable scaling relationship, except these dwarf galaxies don't follow that relationship. Their black holes are far too massive for their host galaxies, which suggests either the black holes formed first and the galaxies grew around them, opposite the usual sequence, or some process allows certain small galaxies to grow disproportionately massive black holes. Either scenario challenges standard models of galaxy black hole coevolution. We thought we understood how galaxies and their central black holes grow together, each influencing the other through feedback mechanisms. These dwarf galaxy observations suggest that understanding is incomplete. The pattern repeats across Webb's discoveries. Supermassive black holes appearing just 570 million years after the Big Bang, far earlier than conventional black hole growth models allow. Galaxies converting gas to stars with impossible efficiency, structures that shouldn't exist yet appearing fully formed in the universe's infancy. Each individual observation might have some explanation within existing frameworks, but collectively, they paint a picture of an early universe that simply didn't behave like our theories predict. Not in one specific way, but across multiple independent processes. That's what makes this genuinely interesting rather than just puzzling. If Webb found one type of anomaly, you'd focus on that specific mechanism. But when multiple different observations from independent research teams all point toward the same conclusion, that the early universe was fundamentally different, you start questioning more basic assumptions. Maybe star formation physics changes at high redshift due to different gas properties. Maybe dark matter halos were denser or distributed differently. Maybe black holes grew through pathways we haven't identified. Maybe feedback mechanisms operated differently. Maybe some combination of all these factors, each contributing to the discrepancies Webb observes. Or maybe, and this is the possibility that keeps cosmologists awake at night, maybe the constants we assume are constant actually varied in the early universe. The strength of fundamental forces, the masses of elementary particles, even the cosmological constant itself might have been different 13 billion years ago. That seems radical. It is radical. Varying constants open doors to physics we've deliberately kept closed because allowing them makes theories unfalsifiable. You can explain anything if you're willing to adjust fundamental constants. So science generally resists that option until all alternatives exhaust themselves. We're not there yet, but Webb is pushing us closer to that boundary than we've been before. The early universe's behavior increasingly looks like it might require something beyond tweaking astrophysical models, something that touches the foundations of physics itself. Assuming varying constants sounds desperate, a last resort when everything else fails. But it's not quite as radical as it first appears. We already know certain constants aren't absolutely constant across all conditions. The fine structure constant, which determines electromagnetic interaction strength, shows tiny variations when measured at different energy scales. Particle masses change depending on the Higgs field's local properties. Even time runs differently in strong gravitational fields. So the concept of parameters varying under extreme conditions isn't foreign to physics. The question is whether variations large enough to affect early universe evolution are permitted. Most physicists remain skeptical, not because varying constants are impossible in principle, but because invoking them becomes a get-out-of-jail-free card. Any observation that contradicts theory can be explained by adjusting the right constant at the right time. That path leads nowhere productive. You end up with unfalsifiable theories that predict nothing and explain everything. Science requires constraints, models that make specific predictions you can test. Allowing fundamental parameters to vary freely removes those constraints. Still, when multiple independent lines of evidence all point in the same direction, you have to consider possibilities you'd normally dismiss. Webb isn't just finding one type of anomaly. It's finding structure forming too quickly, black holes growing too fast, stars burning too bright, galaxies assembling too efficiently, all in the same epoch. That pattern suggests something systematic, rather than isolated problems with individual astrophysical models. Here's what makes the situation genuinely uncertain rather than just confusing. The early universe physics we're observing occurred under conditions we can never replicate. No laboratory on Earth can recreate temperatures of billions of degrees, densities approaching nuclear matter, or gravitational fields strong enough to warp space-time significantly. We test our theories against particle accelerator data, which reaches impressive energies, but nowhere near Big Bang conditions. The first seconds after the universe began remain forever beyond direct experimental verification, so we build models, extrapolate known physics to extreme regimes, make reasonable assumptions about how things should behave at energies we can't probe directly. Those models have been remarkably successful. They predicted the cosmic microwave background's properties before we measured it, explained element abundances from Big Bang nucleosynthesis, and described structure formation at scales we can observe locally. But now Webb is testing those models in regimes they were designed to describe and finding discrepancies. The discrepancies aren't random. They cluster around galaxy formation processes in the universe's first billion years. After that epoch, things start matching predictions reasonably well. Modern galaxies look like we expect them to. Intermediate age galaxies show properties consistent with gradual evolution from early forms to present-day structures, but push back beyond about 1 billion years after the Big Bang. And the observations increasingly diverge from expectations. That temporal boundary matters. It suggests whatever physics operated differently in the early universe either stopped operating differently after sufficient time passed, or its effects became negligible once certain conditions changed. Temperature dropping below critical thresholds, perhaps. Or dark matter halos reaching sizes where different dynamics dominate. Or feedback processes becoming efficient enough to regulate star formation. Something about the universe crossing from its infant state to its adolescent phase fundamentally altered how galaxies assembled. 3 broad categories of explanation remain plausible. First, astrophysics in the early universe genuinely differed from today in ways our models don't capture. Stars formed through different pathways. Black holes grew via mechanisms we haven't identified, or gas physics behaved differently at high redshift. This option requires modifying or extending astrophysical theory, but leaves fundamental physics intact. Second, our understanding of dark matter is incomplete. Not wrong necessarily, but missing crucial details about how dark matter halos formed, how they concentrated, or how they interacted with ordinary matter in the early universe. Dark matter remains the most mysterious component of cosmology, despite being the dominant form of matter. We've never directly detected a dark matter particle. We infer its existence from gravitational effects. Perhaps those effects operated differently when the universe was denser and hotter. Third, something about fundamental physics changed between the early universe and today. constants that aren't quite constant, forces whose strength varied with cosmic conditions, or entirely new physics that operated at energies present shortly after the Big Bang, but irrelevant in the cooler universe we inhabit now. This option is the most radical, but potentially explains why multiple independent processes all show anomalies in the same epoch. Webb can't distinguish between these categories through observation alone. You'd need to test predictions from each framework against future data, seeing which models successfully explain new observations. That process is underway now. Theorists are developing refined models incorporating bursty star formation, different dark matter properties, or modified physics at high redshift. Each model makes specific predictions about what Webb should find as it continues observing. The telescope has only been operational for about 3 years. Its mission is designed to last at least 10, possibly longer with proper fuel management. Every additional year of observations provides more data, more galaxies at extreme distances, more detailed spectroscopy of their properties, more statistics to distinguish real trends from noise. The sample size increases, the uncertainties shrink, and gradually, certain theories will either match the growing dataset or fail to explain it. That's how science progresses when confronting genuinely new phenomena. Initial observations create puzzles. Theorists propose multiple explanations. Further observations eliminate some possibilities while supporting others. Eventually, a consensus emerges. Not because one camp wins an argument, but because the data increasingly favor certain interpretations over alternatives. We're still in the early phase of that process with Webb's early universe discoveries. The puzzles are clear. The proposed explanations are numerous. But the data remains insufficient to definitively choose between them, which makes this an unusually exciting time in cosmology. We know we're missing something important. We have multiple candidates for what that something might be, and we have the observational tools to eventually figure out which candidate is correct. The situation differs completely from previous observational surprises in astronomy. When pulsars were discovered in 1967, they were initially mysterious but quickly explained. Rotating neutron stars whose beams sweep past Earth like cosmic lighthouses. The explanation fit existing physics perfectly. When cosmic acceleration was discovered in 1998 through supernova observations, it contradicted expectations, but could be accommodated by adding dark energy to cosmological models. Surprising, yes. Paradigm shifting, absolutely, but not requiring entirely new physics. Webb's early universe observations feel different. They're not one discovery requiring one explanation. They're multiple observations across different research areas, all pointing toward the same conclusion. The early universe didn't behave like our theories predict. And the explanations being proposed aren't minor adjustments. They're fundamental questions about star formation physics, dark matter properties, and potentially the constancy of natural laws. Some astronomers find this situation exhilarating. The opportunity to witness a genuine revolution in understanding doesn't come often. Most careers in science involve incremental progress, small improvements to existing models, modest extensions of known theory. Actually discovering that something fundamental is wrong with current understanding is rare. If Webb's observations truly require revising basic assumptions about how the universe evolved, that's the kind of breakthrough scientists dream about being part of. Others find it frustrating. Decades of work developing and testing the standard cosmological model suddenly face challenges from observations that don't fit. Theories that seemed well established require modification or replacement. Graduate students whose thesis projects assumed certain physics now have to reconsider their foundations. It's uncomfortable when the ground shifts beneath established science, but discomfort often precedes progress. The most significant advances in physics frequently emerged from observations that didn't match theory. When Mercury's orbit didn't quite follow Newtonian predictions, it seemed like a minor anomaly, probably some undiscovered asteroid perturbing its motion. Instead, it was the first hint that general relativity was needed. When galaxies rotated too fast to be held together by visible matter, it seemed like an observational error. Instead, it was evidence for dark matter. When the cosmic microwave background showed temperature fluctuations at specific scales, it seemed puzzling. Instead, it confirmed inflation theory. Webb's early universe observations might join that list. Anomalies that seemed confusing initially, but eventually revealed something profound about how reality works. Or they might turn out to be less revolutionary, explained through refinements to existing models without requiring fundamentally new physics. We don't know yet. That uncertainty is what makes following Webb's discoveries compelling, rather than just technically interesting. The telescope continues observing. Every few months, new papers appear analyzing its data. Some confirm earlier findings with better statistics. Others discover entirely new phenomena that previous instruments couldn't detect. The picture of the early universe grows more detailed, but also more puzzling, as each observation reveals unexpected features. And gradually, that accumulation of detail will narrow the possibilities. Theories that predicted certain features Webb doesn't observe will be abandoned. Models that successfully explain multiple independent observations will gain support. The question of whether cosmology needs revision or just refinement will eventually have an answer, not through philosophical debate, but through the steady accumulation of evidence that favors some explanations over others. That's what distinguishes this era from previous periods of cosmological uncertainty. We're not just speculating about the early universe. We're directly observing it with unprecedented clarity. The answers to questions about galaxy formation, black hole growth, and star formation physics are encoded in the light Webb collects. They're not philosophical puzzles. They're empirical questions with definitive answers waiting to be extracted from data, which brings us to perhaps the most remarkable aspect of Webb's mission. The telescope isn't just challenging our understanding of the early universe. It's revealing that the universe has more stories to tell than we anticipated. Every time we've built more powerful observational tools, we've discovered phenomena nobody predicted. Radio astronomy revealed pulsars and quasars. X-ray astronomy found neutron star binaries and hot intergalactic gas. Infrared astronomy showed us dust-enshrouded star formation. Gravitational wave astronomy detected merging black holes. Webb continues that tradition. Its infrared capabilities and sensitivity weren't just designed to observe known phenomena more clearly. They opened a window onto aspects of the universe we didn't know existed. The little red dots, the ultramassive early galaxies, the supermassive black holes in dwarf systems. None of these were predicted before Webb launched. They emerged from the data, surprises that revealed how much we still don't understand. That pattern of discovery, finding things we didn't predict, reveals something fundamental about scientific progress. We don't advance primarily by confirming what we already think we know. We advance by encountering phenomena that don't fit existing frameworks, then figuring out what those phenomena are telling us about reality. Webb's true value isn't measuring known objects more precisely. It's showing us aspects of the universe we weren't looking for because we didn't know they existed. Consider the cosmic microwave background. Before its accidental discovery in 1965, cosmologists debated whether the universe had a beginning or existed eternally. The CMB settled that question definitively, not through philosophical argument, but by providing direct evidence of a hot, dense early state. Similarly, Webb isn't settling debates through better arguments. It's providing observational constraints that force certain conclusions, regardless of theoretical preferences. The telescope's impact extends beyond what it directly observes. Each discovery constrains theories about adjacent phenomena. Finding supermassive black holes at extreme distances doesn't just tell us about black hole formation. It constrains how quickly gas could cool and collapse in the early universe, which affects models of the first stars, which influences predictions about chemical enrichment, which shapes expectations for galaxy evolution. Everything connects. This interconnectedness means that explaining one Webb discovery often requires revising assumptions about seemingly unrelated processes. The little red dots initially appeared to challenge galaxy formation theory. Their resolution through supermassive black holes raises questions about how those black holes formed so quickly. Answering that might require revising star formation models. Changing star formation assumptions affects predictions about cosmic chemical evolution. The solution to one puzzle creates entry points into others. That cascade of implications makes Webb's observations particularly valuable. A telescope that merely confirmed existing predictions would be scientifically useful, but wouldn't drive progress as dramatically. One that reveals unexpected phenomena forces the entire field to reconsider its assumptions, opening research directions nobody had planned to explore. The telescope has also revealed that our observational capabilities were more limited than we realized. Before Webb, astronomers thought they had a reasonably complete census of galaxy populations in the early universe, with Hubble providing the deepest views available. Webb's first images showed that assessment was premature. Entire categories of objects, faint galaxies, dust-obscured systems, distant red sources, were invisible to previous instruments, but turn out to be numerous and important. This pattern has repeated throughout astronomical history. Every major observational advance reveals that the universe contains more than we thought. Radio telescopes discovered quasars and pulsars. X-ray observatories found hot gas between galaxies. Infrared surveys revealed dust-shrouded star formation. Gravitational wave detectors showed us merging black holes we couldn't see electromagnetically. Each new window onto the universe reveals phenomena that were always there but undetectable with previous tools. Webb continues that tradition, but with a twist. Previous observational advances typically opened entirely new wavelength regimes: radio, X-ray, ultraviolet. Webb observes in infrared, a wavelength range that's been studied for decades. Its revolutionary impact comes from combining unprecedented sensitivity with infrared wavelengths that penetrate cosmic dust and access extremely redshifted light. It's not seeing a fundamentally different kind of radiation. It's seeing familiar radiation from objects that were too faint, too distant, or too obscured for earlier instruments. That makes Webb's discoveries particularly interesting. They're not revealing exotic phenomena requiring new physics to explain. They're showing that familiar processes, star formation, black hole accretion, galaxy assembly, operated differently in conditions we couldn't previously observe. The universe's early history isn't written in some alien physics we've never encountered. It's written in the same physics we study locally, but applied in extreme environments we're only now able to access observationally. This distinction matters because it means Webb's discoveries should be explainable using known physics, just applied in unexpected ways. We don't need to invoke entirely new fundamental forces or particles. We need to understand how gravity, gas dynamics, nuclear fusion, and electromagnetic radiation behaved when the universe was younger, denser, and hotter than anything we can recreate experimentally. That's both encouraging and challenging. Encouraging because it means the tools for explaining Webb's observations already exist. They just need to be applied correctly. Challenging because it requires detailed physical modeling of processes that are difficult to simulate. Star formation in turbulent, metal-poor gas. Black hole growth in environments with different radiation backgrounds. Galaxy assembly through mergers when objects were closer together. Each process operates according to physics we understand in principle, but struggle to model accurately in practice. The computational demands are substantial. Simulating galaxy formation from first principles requires tracking gas dynamics, star formation, stellar evolution, supernova feedback, black hole accretion, radiation transport, and chemical enrichment simultaneously across vast ranges of scale, from individual stars to galaxy clusters. Current simulations make simplifying assumptions that might miss crucial physics. As observations become more detailed, those assumptions become harder to justify. Webb's data quality creates both opportunity and pressure. Opportunity, because precise observations constrain models effectively. Pressure, because models that worked adequately when observations were uncertain now face stringent tests they often fail. A simulation that reproduces galaxy masses to within a factor of 2 seemed acceptable when observational uncertainties were large. When Webb measures masses to 20% accuracy, factor of 2 discrepancies become problematic. This drives a productive cycle where observations motivate better models, which make testable predictions, which observations then confirm or refute. That cycle has accelerated dramatically since Webb started operating. Papers analyzing its data appear weekly. Some confirm earlier findings with better statistics. Others discover entirely new phenomena. Each observation narrows the space of viable theories. The telescope has also democratized access to high-quality data in unexpected ways. While telescope time remains competitive, Webb's data becomes publicly available relatively quickly. Astronomers who didn't participate in original observations can analyze archival data, often discovering things the original observers didn't notice. This crowdsourced analysis has already yielded significant findings, including some of the little red dots, which were identified in datasets collected for other purposes. That openness accelerates progress. Instead of discoveries being limited to teams with telescope access, anyone with appropriate expertise can analyze Webb's observations. This distributes the work of understanding its discoveries across the global astronomical community. Someone studying galaxy evolution might notice a faint object in the background of their target image. That background object could turn out to be a distant quasar or a gravitationally lensed galaxy, or an entirely new phenomenon. Webb's mission timeline adds another dimension to its impact. The telescope is designed to operate for at least 10 years, possibly longer if fuel reserves last. Each year of operation will roughly double the accumulated exposure time on key fields, improving signal-to-noise ratios and enabling detection of even fainter objects. Discoveries made in year 1 will be refined in year 3 and potentially superseded by year 7 as deeper observations reveal more detail. This extended timeline means that many questions Webb raises won't be answered quickly. The telescope will continue surprising us throughout its operational lifetime. Early discoveries that seemed anomalous might turn out to be representative once larger samples accumulate. Or they might remain outliers, requiring special explanation. We won't know until sufficient data exists to characterize object populations statistically rather than anecdotally. The telescope's observations also have implications beyond cosmology. By revealing the chemical composition of the early universe through spectroscopy of distant galaxies, Webb constrains models of nucleosynthesis, the process by which elements heavier than hydrogen and helium formed. Those elements are crucial for planet formation and eventually for life. Understanding when and how carbon, oxygen, nitrogen, and iron became abundant in the universe connects directly to questions about habitability and the conditions necessary for complex chemistry. Webb has already detected organic molecules in distant galaxies, showing that the chemical ingredients for life existed earlier than previously documented. This doesn't imply life itself formed that early. Conditions in the dense, radiation-flooded environment of the early universe were likely hostile to biology. But it establishes that the raw materials became available quickly after the first stars began producing heavy elements. These connections between Webb's cosmological observations and questions about life's origins illustrate how astronomical discoveries have implications far beyond their immediate context. A telescope designed to study galaxy formation ends up informing our understanding of chemistry, stellar evolution, planetary science, and potentially biology. That's characteristic of fundamental research. Insights gained in one domain often prove relevant to questions that seem entirely unrelated. The telescope has also revealed the importance of dust in the early universe. Many of the brightest objects Webb detects are heavily obscured by cosmic dust, tiny particles of carbon and silicates that absorb ultraviolet and visible light while emitting infrared radiation. This dust forms in stellar atmospheres and supernova ejaculation, gradually enriching the interstellar medium with solid particles. Webb's infrared vision penetrates this dust, revealing star formation that would be completely invisible at shorter wavelengths. The presence of substantial dust in early galaxies was unexpected. Dust requires heavy elements, which only form in stars. But Webb sees dusty galaxies just hundreds of millions of years after the Big Bang, seemingly too early for multiple generations of stars to have lived and died, producing the metals necessary for dust formation. Either the first stars produced metals more efficiently than expected, or dust forms more quickly than models predict, or some other process accelerated chemical enrichment. That mystery connects to broader questions about how the universe transitioned from its initial composition, roughly 75% hydrogen and 25% helium by mass, to the chemically diverse cosmos we inhabit today. Every atom of carbon in your body, every oxygen molecule you breathe, Every calcium atom in your bones formed inside a star or during a supernova explosion. Webb's observations of the early universe show that process of cosmic chemical enrichment began almost immediately after the first stars formed. Understanding that timeline matters for assessing how common Earth-like planets might be. If metal enrichment happened quickly, then rocky planets could have formed early in cosmic history. If it took billions of years, then potentially habitable worlds became common only recently. Webb's observations of dust and metals in early galaxies provide crucial data for estimating when planetary systems like our solar system could have first appeared. The telescope's discoveries also have philosophical implications about our place in cosmic history. If we live relatively early in the universe's history, when less than 10% of potential stars have formed, then we're among the first generations of complex life to emerge. If we live late, when most star formation is past, then we might be unusual stragglers in a universe that was once far more active. Webb's measurements of star formation rates at different cosmic epochs help map where we sit in that timeline. Current observations suggest we live around cosmic noon, the period when star formation peaked, but that conclusion might change as Webb observes more distant epochs. The telescope has already shown that star formation began earlier and more vigorously than previous instruments could detect. Whether that trend continues even earlier remains to be determined. These questions about cosmic timelines and our place within them illustrate how Webb's technical observations connect to profound questions about existence. A measurement of galaxy brightness at high redshift doesn't just constrain astrophysical models. It tells us something about when conditions suitable for life became common in the universe, about whether we're typical or unusual, about what came before us and what might come after. That's what makes following Webb's discoveries compelling rather than just technically interesting. The scale of cosmic time reveals something unsettling about observation itself. We don't just see distant galaxies as they were. We see them frozen at specific moments, unable to know what happened next. That galaxy forming stars furiously 12 billion years ago might have evolved into something magnificent, or it might have collided with a neighbor and been destroyed entirely. The light reaching us now carries no information about its fate. Webb's observations create a vast archive of cosmic snapshots, each one capturing a moment that will never be repeated, a configuration of matter that existed once and then transformed into something else. This temporal limitation affects how we interpret what Webb shows us. When astronomers identify what appears to be an extremely massive galaxy in the early universe, they're seeing that galaxy at one specific moment in its evolution. Perhaps it was experiencing an unusual burst of star formation that week, cosmically speaking, and normally looked quite different. Or maybe it was in the process of merging with another galaxy, temporarily appearing more massive than it truly was. We have no way to watch that galaxy over time, to see whether its apparent properties represent a stable configuration or a transient phase. Every observation is a single frame from a movie we'll never see in motion. That constraint shapes the kinds of questions Webb can answer. The telescope excels at revealing what existed at different cosmic epochs, but struggles to show us how individual objects evolve from one state to another. We can observe a galaxy at redshift 10 and another at redshift 5, but we can't follow a single galaxy through that transition. Instead, astronomers must build statistical arguments, studying large samples of galaxies at different times and inferring evolutionary patterns from population-level changes. That approach works remarkably well for understanding general trends, but leaves gaps when it comes to rare events or unusual objects. The discovery of those little red dots, compact sources that might be supermassive stars or black holes, illustrates this challenge perfectly. These objects appear only at very early cosmic times, suggesting they represent a brief phase in the evolution of something. But what happens to them? Do they collapse into black holes? Do they explode? Do they gradually settle into more ordinary configurations? Webb can show us they existed, but not what they became. That uncertainty makes interpreting their significance difficult. If they're a common but short-lived phase that many early galaxies pass through, they might not require any dramatic new physics. If they're rare anomalies that represent unusual conditions, they might point toward processes we don't yet understand. The telescope's observations also reveal how cosmic recycling operates on the largest scales. When a massive star explodes, it doesn't just create a spectacular light show, it also enriches the surrounding gas with heavy elements that will eventually form new stars and planets. Webb's detection of substantial dust and metals in early galaxies shows that recycling process began almost immediately after the first stars formed. But the efficiency of that recycling depends on many factors. How much material does a supernova actually eject into the surrounding space versus swallowing back into the collapsing core? How quickly do those ejected elements mix with pristine gas? How many stellar generations does it take to build up the chemical diversity we see in the solar system? Those questions connect directly to habitability. Rocky planets like Earth require substantial amounts of silicon, iron, and other heavy elements. If metal enrichment happened slowly, taking billions of years to produce sufficient heavy elements, then potentially habitable worlds became common only recently in cosmic history. If it happened quickly, with early stars efficiently producing and distributing metals, then Earth-like planets might have formed throughout much of the universe's history. Webb's observations of dust and metals in galaxies less than 1 billion years old suggest the enrichment process was faster than many models predicted. That implies rocky planets could have formed quite early, though whether any of them developed conditions suitable for life remains unknown. The telescope has also begun revealing how galaxy mergers shape cosmic evolution. When two galaxies collide, their stars rarely hit each other directly. Space is simply too empty for stellar collisions to be common, but their gas clouds compress and shock, often triggering intense bursts of star formation. Webb's infrared vision can peer through the dust generated by these mergers, revealing star formation that optical telescopes would miss entirely. Early observations show that mergers were indeed common in the young universe, with many galaxies displaying disturbed shapes and multiple nuclei indicating recent or ongoing collisions. That validates theoretical predictions that galaxies grow partly through merging, gradually assembling from smaller building blocks. But merger dynamics turn out to be more complex than simplified models suggested. The outcome of a collision depends on the mass ratio between the galaxies, their internal structure, the angle and speed of the collision, and the amount of gas each galaxy contains. Sometimes mergers trigger starbursts that consume most available gas within a few 100 million years. Sometimes they funnel gas towards central black holes, creating luminous quasars. Sometimes they actually suppress star formation by shocking gas to such high temperatures it can't cool and condense. Webb's observations are beginning to map this diversity of outcomes, showing that galaxy mergers don't follow a single script but produce varied results depending on initial conditions. The discovery of massive black holes in small galaxies raises particularly interesting questions about how black holes and galaxies co-evolve. In large galaxies, there's a tight correlation between black hole mass and the properties of the surrounding stellar bulge, suggesting they somehow regulate each other's growth. But in dwarf galaxies, small systems with relatively few stars, that correlation breaks down. Some dwarfs contain black holes far more massive than expected given their stellar mass. How did those black holes grow so large in such small galaxies? Did they form massive from the start, perhaps from the direct collapse of primordial gas clouds? Or did they grow through unusually efficient accretion, somehow gathering mass faster than their host galaxies grew stars? Webb's discovery of these overmassive black holes in dwarfs might point toward different formation channels operating in the early universe versus today. Perhaps the very first black holes formed through mechanisms unavailable in the modern universe, when gas was hotter and more pristine. Or perhaps black holes in small galaxies are particularly efficient at accreting gas because they face less competition from star formation. Understanding these systems matters for predicting how many intermediate mass black holes, objects between stellar mass black holes and supermassive ones, should exist in the universe. Current observations find fewer than expected, a puzzle that might be resolved by recognizing that some grew massive while remaining in relatively small galaxies. The 7-hour gamma-ray burst Webb helped characterize represents another category of cosmic puzzle: transient events that don't fit existing models. Gamma-ray bursts are already extreme phenomena, releasing as much energy in seconds as the Sun will emit over its entire lifetime. The Standard Model explains short bursts as neutron star collisions and long bursts as massive stellar collapses. But a 7-hour burst? That duration suggests something fundamentally different, perhaps a new class of event we haven't recognized before. The burst's properties, including X-ray activity detected a day earlier, hint at a more complex process than the clean scenarios in textbooks. Events like this remind us that the universe contains phenomena we haven't catalogued yet. Our theoretical frameworks are built from observed examples, but we've only been watching the cosmos systematically for a few decades. The universe is 13.8 billion years old and contains trillions of galaxies, each one potentially hosting rare events. Some phenomena might be so unusual or so brief that humans have never witnessed them before. Webb's combination of sensitivity and infrared capability means it can detect exotic events previous telescopes would have missed entirely. As the telescope continues operating, it will likely find more objects that don't fit existing categories, forcing astronomers to expand their understanding of what's possible. The possibility of dark stars, objects powered by dark matter annihilation rather than fusion, illustrates how Webb's observations might eventually point toward physics beyond the Standard Model. If those early bright galaxies really were powered by dark matter, it would be the first direct detection of dark matter beyond its gravitational effects. That would revolutionize particle physics, finally revealing what constitutes the majority of the universe's mass. But the case for dark stars remains speculative. The observations could also be explained through more conventional physics, involving massive stars and black holes. Distinguishing between these possibilities will require more data and careful analysis. What makes Webb's contribution particularly valuable is its ability to gather spectroscopic data on faint, distant objects. A spectrum, the breakdown of light into its component wavelengths, reveals an object's composition, temperature, motion, and physical conditions in ways that simple images cannot. Webb's spectrographs can detect specific emission lines from elements like oxygen, carbon, and iron in galaxies billions of light-years away, allowing astronomers to measure their chemical composition directly rather than inferring it from brightness and color. That capability transforms our understanding of cosmic chemical evolution, showing not just that metals existed in the early universe, but exactly which elements were present and in what proportions. The telescope's mapping of dark matter distribution provides another example of how infrared observations reveal hidden structure. Dark matter doesn't emit light at any wavelength, but its gravitational effects bend the light from background galaxies, creating subtle distortions that can be measured. By analyzing how light from distant galaxies is warped as it passes through intervening dark matter, astronomers can map that invisible matter's distribution. Webb's sharp infrared images show many more background galaxies than visible light telescopes can detect, providing more data points for dark matter mapping. The resulting maps reveal dark matter's filamentary structure in unprecedented detail, confirming that it forms the scaffolding around which ordinary matter accumulates. These dark matter maps also offer a new way to test cosmological models. The standard lambda-CDM model makes specific predictions about how dark matter should cluster at different scales. Webb's observations allow astronomers to measure that clustering at high redshift, testing whether dark matter behaved in the early universe as models predict. So far, the observations match predictions reasonably well, supporting the standard model's validity. But small discrepancies at certain scales might eventually point toward modifications needed to reconcile theory with observation. As Webb continues gathering data, the pace of discovery shows no signs of slowing. The telescope has now been operating for over 3 years, long enough to begin studying how objects change over time. Some quasars have brightened or dimmed. Some galaxies have been observed at multiple epochs, showing how their star formation rates evolve. Some gravitational lensing events have shown time-varying magnification as foreground objects move. These temporal measurements add a new dimension to astronomy, allowing scientists to watch the universe change rather than just seeing static snapshots. The telescope's instruments remain in excellent health, performing as well as, or better than expected before launch. Barring unexpected failures, Webb should continue operating for at least another decade, possibly longer. That longevity matters for studying rare events and tracking long-term changes. Some phenomena only reveal themselves through patient observation over years. Some questions require accumulating vast amounts of data to achieve the statistical precision needed for definitive answers. Webb's extended mission will allow astronomers to pursue investigations impossible with shorter observing campaigns. But perhaps the most important contribution Webb makes isn't any specific discovery. It's the shift in perspective the telescope enables. Before Webb, the universe beyond redshift 10 was largely theoretical territory, a realm we could model but not observe. Now it's real, populated by actual galaxies we can study, That shift from abstraction to empirical data changes how astronomers think about cosmic history. The early universe is no longer a theoretical construct, but a place we can visit with our instruments, even if only with ancient light. That access to cosmic dawn completes our view of the universe's full history, connecting the physics of the Big Bang to the galaxies we see around us today. And in that connection, that unbroken chain of cause and effect, stretching from the first stars to the present moment, we find our own origin story written in light that has traveled for most of the universe's lifetime to reach us. Every discovery Webb makes raises 10 new questions. That pattern won't change as the telescope continues observing. We're not approaching some final understanding of the early universe. We're discovering how much stranger and more complex it was than we imagined. The galaxies that appeared too massive, the black holes that formed too quickly, the structures that assembled too efficiently, each one reveals that our models captured part of the story, but missed crucial details. The resolution of the apparent cosmological crisis doesn't mean the mysteries vanished. It means we've learned to ask better questions. Instead of, does the standard model survive? We're now asking, what specific processes in the early universe operated differently than today? That's progress. Moving from wholesale doubt about fundamental frameworks to detailed questions about specific mechanisms. But here's what keeps astronomers genuinely unsettled. The early universe wasn't just quantitatively different, slightly more efficient at forming stars, moderately more effective at growing black holes. It was qualitatively different. The physics operated in regimes we can't test experimentally. The conditions were more extreme than anything we can recreate. And the outcomes, those impossibly bright galaxies, those supermassive black holes appearing in cosmic infancy, those turbulent systems that somehow produce stable structures, challenge our understanding in ways that go beyond tweaking parameters in existing models. Webb has shown us that the universe's first billion years were wild. A cosmic adolescence when everything happened faster, brighter, more violently than the stately evolution we observe in mature galaxies. Stars formed in bursts that would tear apart modern galaxies. Black holes grew through mechanisms we're still trying to identify. Galaxies collided and merged at rates that make today's cosmic environment seem almost static, and we're only seeing a fraction of what existed. Webb observes a tiny patch of sky at extreme distances, detecting only the brightest objects from that era. Fainter galaxies, smaller black holes, less dramatic events remain beyond even its remarkable capabilities. The cosmic census remains incomplete. What we've found so far might not be representative. These could be the outliers, the exceptional cases that caught our attention because they're unusual. Or they might be typical, with countless similar objects waiting to be discovered once we look deeper. That uncertainty will persist for years. Even after a full decade of Webb observations, questions will remain. Some objects will defy explanation. Some patterns will resist interpretation. That's not a failure of the mission or the science. It's a recognition that the universe is larger and older than any telescope can fully survey. That some phenomena remain rare enough that we might never observe them. That some processes operated only briefly during cosmic history before conditions changed. The telescope has also revealed something about the practice of astronomy itself. For decades, cosmologists built increasingly sophisticated models, running simulations on supercomputers, predicting what early galaxies should look like. Those models were educated guesses, constrained by theory, but not by direct observation of the objects they described. Webb changed that. Now we have data. Real measurements of real galaxies from that era. And the data doesn't entirely match the predictions. That discrepancy is valuable. It shows which assumptions in our models were correct and which need revision. But it also reveals how much we were extrapolating beyond what we actually knew. The early universe wasn't just the modern universe run backward. It had its own character, its own dynamics, its own rules that emerge only when you actually observe what happened rather than calculating what should have happened. Scientists sometimes talk about nature being cleverer than we are, finding solutions we wouldn't have predicted. The early universe exemplifies that. However galaxies formed so quickly, however black holes grew so massive, however stars assembled with such efficiency, nature found pathways that weren't obvious from theoretical considerations alone. Webb is showing us those pathways, though we're still working out the details. The discoveries also remind us that our position in cosmic history gives us a privileged view. We live at a time when the cosmic microwave background remains observable, when distant galaxies are still visible before cosmic expansion carries them beyond our horizon, when the chemical composition of ancient stars preserves clues about nucleosynthesis in the early universe. 100 billion years from now, if any astronomers exist in our galaxy, they won't have access to these observations. The CMB will have redshifted into undetectability. Distant galaxies will have receded beyond the observable universe. The oldest stars will have died. Future scientists will face a much harder task reconstructing cosmic history because the evidence will have faded. We're fortunate to inhabit an era when the universe's story remains legible. And we're fortunate to have built a telescope capable of reading the earliest chapters of that story, even if we're still learning the language in which those chapters are written. The next few years will bring more surprises. Webb will find galaxies at even higher redshifts, pushing closer to the epoch when the first stars formed. It will discover more exotic objects that don't fit existing categories. It will reveal details about the early universe that we haven't thought to predict, because we don't yet know what questions to ask. Each discovery will refine our understanding, while simultaneously revealing new gaps in that understanding. That's the nature of exploration at the frontiers of knowledge. You don't find answers that resolve all mysteries and complete the picture. You find answers that lead to deeper questions, that reveal layers of complexity you hadn't anticipated, that show you how much further the mystery extends than you realized. Webb is taking us to those frontiers, showing us phenomena that existed when the universe was young and strange, forcing us to expand our conception of what's possible. And somewhere in that ancient light, in the spectra of those distant galaxies, in the patterns of how structure assembled across cosmic time, lie clues to questions we haven't fully formulated yet. Questions about how matter organized itself from primordial simplicity to the complex structures we observe today. About how the seeds of galaxies like the Milky Way were planted in the chaos of cosmic dawn. About whether the universe has always played by the rules we observe locally, or whether its laws evolved as conditions changed. Those questions don't have simple answers. They require decades of observation, sophisticated modeling, and probably insights we haven't developed yet. But they're now answerable in principle, because Webb has given us access to the era when those processes occurred. The early universe isn't theoretical anymore. It's observational territory, a place we can study with data rather than just speculation. What scientists feared, that Webb might break cosmology, didn't happen. The Standard Model survived, though it gained some interesting bruises along the way. But what Webb actually delivered might be more valuable than a crisis. It delivered complexity, nuance, evidence that the universe's history was richer and stranger than simplified models suggested. It showed us that the infant cosmos contained multitudes, that it explored many pathways simultaneously, that it created a diversity of objects and structures that we're only beginning to catalogue. The telescope has a decade or more of observations ahead. The early universe still holds secrets that haven't been revealed, objects that haven't been discovered, processes that haven't been witnessed, patterns that haven't been recognized. Webb will continue extracting those secrets from ancient light, gradually building a more complete picture of cosmic dawn. Not a simple picture. Simplicity was never realistic for something as complex as galaxy formation, but a truer picture, grounded in observation rather than assumption. And in the end, that's what makes Webb's discoveries genuinely important rather than just technically impressive. The telescope isn't confirming what we thought we knew. It's showing us what actually happened, forcing us to revise our understanding, to match reality rather than hoping reality matches our theories. That process is uncomfortable for scientists who invested careers in developing those theories. But it's exactly how science is supposed to work. Observation leads, theory follows, and when they diverge, we change the theory because we can't change the observations. The universe that existed 13 billion years ago was wilder than we imagined. Webb has opened a window onto that wildness, revealing a cosmos in its adolescence, turbulent, energetic, excessive, transforming from simplicity to complexity through processes that remain only partly understood. We're privileged to witness that transformation, even if only through the ancient light of galaxies that evolved long ago into something very different from what we observe. Their light carries messages from cosmic dawn, written in the language of photons that have traveled across most of the universe's history to reach our telescopes. And in learning to read those messages, we discover not just what the universe was, but what it might yet become, and what our place might be in a story that's still unfolding across cosmic time.